This second video has to do specifically with sand and how it moves. This should be primarily a review. You guys covered coastal geo quite a bit, but here we go. In order to talk about coastal geomorphology, basically what makes up a beach is sand, so we have to talk about how the sand moves. So we're going to be talking about sand movement, basically perpendicular to shoreline, and then again parallel. So this first part deals with perpendicular, and the reason why the sand moves, as you may remember from when you were a kid and you used to just sit on your butt in the swash, is that waves break and they run up the beach. When they run up the beach, the energy from the wave can carry the sand up the beach or down the beach, erosion such as it is. The word for when a wave breaks and then runs up the beach is swash. This is not a made-up word, it's a real word. Let me underline it. This one right here, swash. And backwash is when the water runs up the beach, it gets pulled back down by gravity, and that's called backwash. I know it sounds like when you spit in somebody's drink. These two mechanisms should sound like they're always equal in terms of their energy load, but they're not. And it's a function of how steep the incline of the beach is and how much it can absorb energy. And when the swash dominates, when we have more energetic swash, you get deposition and the beach gets bigger. And when you have a large amount of backwash, the berm is eroded, and these in New Jersey typically coincide with seasons. And this movement up and down the beach face itself is what produces longshore bars, which become really important for a lot of the characteristics we've talked about in the past with waves. I'm just going to do a quick diagram, and I apologize because this is going. So we have, like, from overhead, I'm not even going to, here's a beach face, not even from overhead, kind of facing. And when a wave break, remember waves tend to come in at a slight angle due to wave refraction. And here's the shoreline. The wave's going to come up mostly straight, not all the way, but mostly straight. And that's due to the wave refracting incompletely, as you know, in reality they tend to do. But instead of the water running back the same way it came, due to the fact that it's gravity that pulls it down, it comes straight back down in relation to the beach face. So this would be our swash, and this would be the backwash. The backwash, when it's really, really strong, sometimes people, like your grandparents, might call it an undertow. So these sort of work in this sort of like zigzag position. This is going to become really important later on when we talk about longshore drift. So when the waves are light and the energy is dissipated as the wave runs up the beach, the sand particles have lots of space, so the beach basically acts as a buffer and absorbs the energy. When this happens, the sand that's being carried up with the swash gets dropped on the beach while the water sort of runs back down through the sand particles. When we have heavy wave activity, there's just not enough beach to absorb all the energy. Yes, some sand is carried up by the swash, but none of the energy is absorbed, and the backwash rushes back and carries even more sand with it. So in the summer, our beaches get very wide, the berm gets bigger, sometimes we have multiple ones like we do now, and we have the bar that used to be offshore. Let me go back a slide so I can show you this. So if we have a beach, oh my goodness, what's going on? If we have a beach with water, when we have light wave activity, the sand that's naturally here in this longshore bar gets picked up and deposited, and the berm grows, right? Ever bigger. And this right here gets smaller. When we have a winter beach, so we have, I'm going to use the pen. We have a fairly large berm, no bar. The waves get bigger. Oh, that's horrific. And as they hit, they cause a much stronger backwash, which carries the sand to the deeper water, where it then deposits it. It drops it because the energy is being absorbed by the water, and the sandbar begins to build up. this is what we would call a winter beach, where it's flat. There's very little berm. On the west coast, sometimes the berm is removed completely and you only see the rocks that are underneath. The beach face is flat, not steep, and we have a longshore bar offshore. I don't think anybody in class surfs, but if you did surf, well, some of you are spongers. If you did surf, you know this is one of the reasons why around here the best waves are frequently found in February, because all winter the storms and the increased wave activity have been making the longshore bar bigger. So when the waves break, they break more steeply and you get a better ride. This diagram just sort of summarizes what you need to know about light wave activity and heavy wave activity. It's just summarizing what we talk about. You need to know the wave energy, the time span for like the wave action itself, the characteristics it results in, and what happens to the berm and the longshore bar. This is a picture on the west coast of a summer beach and a winter beach. It's the same beach. And this was a diagram I tried to draw. Of course, I always draw my diagrams skewed towards New Jersey, so like the beach is on the left. But on the west coast, the sand is so removed from the beach that there's frequently rocks left behind, which you can kind of see in this picture right here. There are algae covered here, but those are rocks, and so the sand gets deposited, and in the winter it gets removed. It's much more dramatic, I think, than it is for us, where we always have sand. It's just how much sand do we have. So we covered the movement of sand perpendicular to shore with a swash, and then I draw that picture for you where the swash runs up at a slight angle and the backwash is straight back, and that's that zigzag appearance. This is going to give rise to the longshore current. The longshore current has a bunch of effects, but here in New Jersey we worry about it because it has to do with erosion. A bunch of you were down Cape May. I keep bringing this up. And the beaches down there get bigger because the longshore current basically from the central part of the state runs south. This longshore current can move massive amounts of sand. Last time I checked, the estimate was in Sandy Hook there are 3 loads of sand equivalent to a school bus deposited at the end of Sandy Hook every day, which is constantly changing the shape of the hook. It has to be dredged because eventually Sandy Hook would touch New York City. This is also occurring down in Cape May area as well. If you've ever been to Wildwood, the beach there is something like a half a mile wide. It's a really long walk from where you would put your towel down to like go back and use the bathroom and get a soda or whatever. There's a couple things here you need to know right in here. When any of these happen, it will increase the longshore current speed. So the steeper the beach, the faster the backwash rushes back, so more sediment is moved, the current moves faster. The bigger the waves, the more the longshore current will run. If you increase the angle, the difference between the swash and the backwash, that's due to the wave refracting, not as bending as well, increases longshore current, and should probably make sense that the more waves you have, the more longshore current you'll have as well. I think this was kind of beaten into your head pretty well, but I'm going to say it again. Longshore current and longshore drift are not interchangeable in a marine science class. Longshore current is the movement of the water, specifically in the surf zone. And as I'm sure you remember, the surf zone is the area from the bar to the shoreline. Longshore drift is the movement of the sediment, the sand usually, due to the longshore current. And these are 2 different things. Are they related? Absolutely. Are they exactly the same? No. One's the movement of the water. One is the movement of the sediment due to the movement of the water. And that kind of gets important if you were to go into coastal geo in greater detail. I threw rip current and tides on here because they're kind of related to the same thing. Here's a picture of a rip current. Rip currents are related. They have to do with backwash and swash. And these diagrams always leave out what I think is kind of key. If you're a local who uses the beach, you will know that right in here and right in here would be a sandbar with a gap between them. So the swash is running, we got waves coming in from this direction. So the swash is running this way and it's running back. But because of the sandbar, it's kind of trapped. So now not only is it running back, it's running into this current. Even here where you would expect this to come back, this water can't go, it's trapped. So what happens is it also bends back and bends back. And you get a massive flood of water through this one area in between the gaps in the sandbar. One of the ways you can tell a riptide just by looking at it is you'll frequently have normal breakers over the sandbars, while inside you'll have frothy, basically white water, and it'll be foamy. It'll have all the white water in it. Avoid those areas. I know we all think we can swim out of a rip current, but it's better not to have to. So, mostly don't. Again, I'm sure you've heard this to death, but the reason why rip currents kill people is they don't pull you down. There's, like, my grandmother was sure that a rip current, like, sucked you down. That doesn't happen. Rip currents run along the surface. But what they do is they're really strong in one direction. But if you try to swim back against it, the water's going to win. People versus water, water almost always wins. What you have to do is swim perpendicular to the movement of the water. So anytime you can go out this way and go this way, you're going to be able to get out of that. So just, we keep telling you this in case it ever happens to you. I'm waiting for the next slide. The longshore drift, due to the longshore transport or longshore current, is the movement of sediment. And I guess this is a number you should know. It's one of those random abstract numbers. Oh, of course. Hold on. Millions of tons of sediment a year. I don't think it's really possible to estimate how much sand is moved. Let's just settle with a lot. And, we do beach replenishment. New Jersey is a very touchy issue. We know that longshore current occurs here. We know that longshore current leads to longshore drift. You put sand down, it's not going to be where you left it, and it may end up somewhere else. These are the sort of issues that you guys are going to have to face as you get older and become voters and make the decisions for us. So don't mess it up. And then there's a blue box in the book called A Beach, a River of Sand. And this one talks about, now our longshore current and our longshore drift are pretty constant in New Jersey, from basically Manasquan, maybe Barnegat north. The longshore current runs north. From there south, it runs south. And those don't change a lot. It may change daily for a short period of time depending on the wind or the waves, but it's predominantly that way. In other parts of the country, it changes seasonally. So you should look at that blue box so you know that. That's it. We're done.